I'm Professor David Burnett. I'm on the faculty of Electrical and Computer Engineering here at Portland State University. This is Millimeter Motes, where I make a case for getting rid of PCBs forever. I have this goal to get rid of them. I can't stand having this dummy chunk of fiberglass in every electronics assembly that is doing nothing but providing some routing and mechanical stability. We need to be able to get rid of it, but first we need to come up with some interesting circuit design level insights that let us get rid of all the stuff we usually assemble on a PCB. I run what I call the WEST lab, the Wireless Environmental Sensor Technology Lab. I have a lot of examples of environmental sensors, wireless environmental sensors that we have made and could make in the future later on, especially stuff that we can create uniquely with stuff that is designed exclusively in silicon. First off, I want to talk about a little bit about how I got here, because my pre-PhD career is all big stuff with lots of PCBs. I have a couple examples there. I need to introduce the concept of wireless modules in contrast to wireless SoC, systems on chip, the actual chip that you would buy that does RF communication versus a complete system, and how we're kind of comparing these things. Talk about on-chip frequency generation, my favorite research topic. If folks fall asleep during that section, I won't be offended. I understand it's quite dry. It's one of those pivotal, almost mathematical sorts of insights that you need in order to figure out how to get rid of all the stuff that would go on a PCB. And then I'll talk about my hopes and dreams for my research career if folks like the National Science Foundation want to write me a check for several $1 million. If anyone out there has that amount of money and wants to support this sort of research, I'm all ears. So how did I get here? One of my first projects back in college was a long-range bioacoustic system up at University of Washington. This with one of our team members standing here for scale. This would send out a loud acoustic ping, a chirp between 8 and 12 kilohertz. It would travel out something like 2 to 5 kilometers, depending on ocean state, reflect off of fish pods, off of the air-filled swim bladders. We get an acoustic response and figure out how many fish are out there without having to go out and tow a net and pick up the fish and count them. Although we did that for ground truthing. Huge device, horrendously power hungry. One of these two big metal cylinders is a PC-104 stack Linux computer that I was the administrator of. The other stack are all mixed signal digital analog converters and reverse ADCs to do all of the analog interface. Just a horrendous amount of effort. That was really fun, though, and got me started on another set of projects back when I was a member of technical staff at Sandia National Labs. We were designing intertidal intruder detection systems. On land, it's kind of easy to build a fence that works pretty well. In deep water, it's, well, I don't want to say easy, but it's fairly well understood on how to use acoustics to see someone swimming in that intertidal section that's sometimes flooded and sometimes not. All bets are off. And so we were coming up with zillions of ways and testing all over the country. Also super exciting, big engineering, lots of PCBs involved in all this stuff. And then my third big project was this underwater robot that was all custom designed, involving freezing your face off down in McMurdo Station, Antarctica. This picture over here in the corner was taken at 3 in the morning with the team members. Also, right, big underwater, heavy-duty stuff. Of course, what did I do when I went to grad school? I thought, how much bigger are devices getting in the future, right? What is the future? What is the research edge of electrical engineering? And it's not big stuff. In my opinion, it was small stuff. So one of my first projects at the very beginning was the circadian state estimator with a postdoc out of the School of Psychology. We were now kind of broaching, this is about 10 years ago, broaching kind of the subject of wearables. This is when Fitbit stuff was just starting to hit the market, and we were trying to come up with other clever ways of inferring, doing kind of health measurements and figuring out what's going on in the body through non-invasive wearable things at the time. Sleep studies, sleep wearable devices were these giant backpacks that included a rectal thermometer, not exactly something that is going to effectively let you live your life while it's monitoring. It's totally upsetting. In a lot of these sleep studies, women stop ovulating. You just completely mess up the experiment by having these things. So we were trying to figure out how to have smaller, unobtrusive things. We had a couple of generations. Now these same sorts of pieces of technology are integrated in these little ring doodads, but this was one of the beginnings. So this is all going, okay, I built a lot of really big things, and I felt like I was designing essentially the same embedded system over and over and over again to fit into a gigantic machine. But if I wanted to do PhD research, I wanted to figure out what was the new stuff, what was coming out of the pike. And for me, that's biomedical, that's implantable, it's tiny, tiny little chips. And so I was like, I need to get into integrated circuit design. That's where I started to go. So to talk about the innovations that we figured out back during my PhD and that I'm carrying forward here at PSU in these millimeter scale environmental sensors as opposed to meter scale or more environmental sensors, I need to briefly introduce the concept of a wireless module as compared to a wireless SoC. A module is a complete communication system. We've got 3 examples from academia and 3 examples from industry displayed up here. And since something like 2011, right, the Silabs Blue Giga is one of the first Bluetooth low energy modules to come out. They're all kind of a centimeter on a side. And this is still true to this day. If you want to design something that is a complete device, that is a standalone object that does wireless communication, you pair this with a battery of appropriate size, depending on whatever your longevity needs are, you're going to end up with this black plastic rectangle in the middle, maybe one of these metal shields on top in order to get FCC certification, and you're going to need all of these off-chip components that are mandatory to support the SoC. What we ended up doing, and what was secretly pictured on the previous slide, is squishing all this stuff into a single IC. We were able to integrate or eliminate all of the off-chip components that you usually need. Sans antenna, that's one sort of asterisk to a lot of this. If I go back 1 slide, or 2 slides, I pictured the chip to scale up here in the corner. So my dream is to get one of these implanted under my skin someday. As soon as I can figure out how to power it for long enough, then I'll be off to the races. So we ended up, so this is also to scale, right? We've got a couple tens of millimeters, and we got this down to just a couple of millimeters on a side, with no reason why we can't continue to reduce that with smaller and smaller transistor processes. So why have we been, and are we actually to this day, kind of stuck at this approximately 1 centimeter scale? And that's because all this stuff that you need in order to support what I've labeled here as the main radio/processor IC. You've got lots of passives, you've got some terminals. If you want to actually plug something in, you've got to have probably 0.1 inch spacing headers. You've got some sensors, power regulation, and most importantly in these red boxes are the crystals. Most designs require or recommend 2, all of them require at least 1. And the big key innovation that we figured out was that you can do without that crystal oscillator. You can cut it, design a clever circuit to provide feedback and calibration through an alternative method. And if you can eliminate those 2 things, well, the rest of these are a little more easy to integrate, and you end up with something that is just a piece of silicon on top of what I've got pictured here, the smallest, easily accessible off-the-shelf battery, which is a 337 silver oxide battery. So that's the big thing, and there has been a lot of work done in eliminating the crystal oscillator and having so-called free-running oscillators that are just, you power them up, they start up at sort of whatever frequency, and away you go. The thing we were able to figure out is you can still do standards compatible interoperability with commercial stuff. So this chip, if we optically program it, attach it to a power source, it'll start blasting Bluetooth packets that all of our phones can hear, as opposed to having something that starts up at kind of who knows what frequency, and it's not going to be communicating at a recognized standard that is going to be interoperable with the billions of devices we already have out there. So this is the device to kind of cut to the quick, especially in the a little too many slide advances. So it is, if you just look at the list of capabilities off here to one side, it's effectively a wireless microcontroller. It's got an ARM Cortex M0. It's running blazing fast, 20 megahertz. We usually run it at 5, but we don't need a whole lot of horsepower. In fact, we don't want it for the size scales that we're going after. We don't want to be consuming a lot of power, so we clock the CPU way down. A teeny amount, but just enough. Program and data memory, 64K of each. And we need 3 wires. We need battery, plus and minus. We need some power source and some antenna. It turns out an antenna is just a piece of wire, and a good antenna is a piece of wire of appropriate size, but a bad antenna you can fit on top of this chip. We actually just drew a wire bond across the ends of the chip. You end up with something like a 20 dB hit to your link margin, but you can still talk to your phone across a room. It's not catastrophically bad, which is very exciting.
You actually use the bond wire as an antenna?
Yeah, we use the bond wire as an antenna. We just drew it from, I think this is the antenna pin right here, and found a capacitive input somewhere at the other end. It drew this little arc. As I mentioned earlier, it performs badly, but it doesn't perform, not at all. That's the important part. If we attach a proper antenna to it, we get many meters of range, but we get something like 1 meter of range with a bond wire antenna. And that's at 2.4 gigahertz, so we're sort of shooting ourselves in the foot by choosing a wavelength that is much longer than the largest dimension of the chip. If we switch to 24 gigahertz or 60 gigahertz, that's actually well-published information. There are on-chip antennas that have been demonstrated. They work really well. But speaking 2.4 gigahertz was really important from an interoperability standpoint. We all carry zillions of devices that will interop with that. And then also, go ahead, yeah, please.
Did you say they could do 60 gigahertz or 60 megahertz?
I'm saying if you redesigned at 60 gigahertz, you could fit a resonant antenna on chip. Okay. As it stands, you have no hope of fitting a resonant antenna right. 12.5 centimeters is much larger than 2 millimeters, so you just kind of stop.
The previous panel attaches to the wire.
Yeah. And one important bullet here is this runs the IETF standardized OpenWSN wireless mesh networking system that came out of my PhD lab years prior. So this can join an IP network. Each one of these little devices can have an IP6 address and be addressable from out in the world. There's no technical limit to how many devices can be part of a mesh network like this. The commercial implementation says, well, if you're using our proprietary devices, you probably call us if you're going to go do more than 50,000. But there's no, it's a RAM limit basically of the host computer in terms of how many entries it can reasonably have. So anyway, we can power this from a whole bunch of other things, solar arrays, printed batteries, and this is in 65 nanometer CMOS, which for those of you who know, that's big. We redesigned this in 5 nanometer. We can shrink this down. We have redesigned it in 28 nanometer. That was a class that I created about 5 or 6 years ago that just redesigned all these pieces. Yeah, go ahead.
Am I hearing that you have some sort of fab here? Or where's this fab?
Yeah, thankfully we're not trying to fab a couple million or more transistors on our own. This is through TSMC. So the 65 nanometer process was provided through TSMC. 28 nanometer, that redesign for the course was through ST Micro. And as you know, there are several options in terms of fab. It's really just sort of which process are you most familiar with, and which process can you afford, essentially. Yeah.
How, you showed the size of it for the dimensions, but how thick is it? Like, is it the same kind of size as the chip that you'd be like on an RFID chart?
It is. When we order, we backlap it down to 0.3 millimeters in thickness.
And is it single layer or is it multi-layer?
It is, well, I guess it depends on what you mean by single layer or multi-layer. There's a single layer of transistors, and then there's about 10 metal routing layers on top.
Okay.
with an ultra-thick metal layer up at the very top in order to get decent inductor capability. Not great, but okay. Certainly great for on-chip, but not great compared to an off-chip dedicated inductor. All right, so what do you do with this? Well, my favorite one is that you glue it to bees and follow them. There was this problem with invasive insects coming down just across the border of Canada. Vikram Iyer at UW was involved in his own efforts to instrument bees, but we had some friends over at INRI in Paris who were faced with the same problem. And so we shipped the folks, the sort of grad students who came after me, assembled a little kit complete with battery, conductive tape, programmer, the chips, and said, you get into the field, you open this case, follow instructions, glue it to one of these invasive species, and hopefully we can find it. The biggest thing we learned from this is that beeswax is actually a much better adhesive than what we were trying to use. So weirdly enough, beeswax sticks to hornets really well. So the next time we try this, hopefully soon, now that my lab here has produced a new generation of sort of fuselages to power these things, hopefully we'll get another shot soon. So one of the things I want to point out is that through this development, if you can compress your entire design into a single chunk of silicon instead of having a bunch of off-chip components, we can do this thing that I call we have new tiers of capability. The three things that we're trying to improve are lifetime, size, and cost. And we can all already think of designs that are much better in one of these at the cost of the other two. Maybe we can do kind of two at once. And for optimizing two instead of and at the cost of the third, there are some examples, but we can't do all three at once. We can't make a really long-lived, in other words, low power, ultra small, super integrated, and comically inexpensive at scale. If you mass produce these things, we're using giant 12-inch wafer fabs that could churn out millions of these things all at once. We could drive the cost down by kind of a stupendous amount. And this 25-cent number here is not made up. That's a fairly reasonable thing. If we can do just one really well, we can have all sorts of fun applications. But if we do all three, we now can finally glue things to insects and so on and so forth. And I want to note, this is one of the most kind of surprising footnotes whenever I think about this stuff, is that improving in one also can improve the other. For example, if you make a physically smaller chip, if you reduce the form factor of this thing even more, you do reduce the cost per chip because you get more squares chopped out of a 12-inch circle than you would otherwise. So if you can save a little bit in silicon, your per unit cost goes down. Potentially a lower power, if you're able to redesign the circuits and reduce the active power or certainly the sleep power, you shrink the battery, and the battery is most of the design at this point. The battery is most of the design. That makes me really happy because I think besides PCBs being fully eradicated and doing design entirely in silicon, I think these wireless sensor things should be more like rockets. And that is, they should be mostly fuel. And if you need less distance or you need to boost less payload, you just have a smaller thing and you burn less fuel. Our single chip Mote IC, it's 4.2 milligrams. It's pictured here with the smallest easily obtainable button cell battery. But if you want the thing to last twice as long, you just get a battery that's twice as big. And so now your form factor and your mass scale directly with lifetime and application, as opposed to for these really cut down, low power environmental sensor devices. Right now it's mostly a Pelican case, and if there's some battery in there, that's fine, but the volume is this giant box. We want to do away with the box and the PCB and all the off-chip components and leave just some silicon, the thing that's actually doing the work, the silicon, and it's really only the top 10% of the silicon. The rest is dead, so we could shave that even further down and cut more of these milligrams off. And all that's left is the thing that's providing energy. That's the goal, and that's something that we're able to enable here. A little aside on frequencies, thanks to our somewhat late start, I'm going to try to rapidly run through this. If you have a crystal, now this crystal here is part of this phase lock loop. If you have one of those, you have the ability to constrain frequency error and to calibrate a VCO, a voltage controlled oscillator. And if you have something that on chip is running at 2.40000 gigahertz, and it starts to wander because of temperature change, random fluctuations, that crystal is going to provide a signal that goes, no, you're running a little too fast, you're running a little too slow, and it provides this correction. And so you end up with this ceiling of error up here at the loop time constant at the speed at which the PLL is able to run. You cut those out here in the second figure. All you've got is a free running local oscillator, and so as it accumulates error, there's nothing to fix it. That's something we don't necessarily want. It's really important to have an accurate sense of time when you're doing wireless communication, because wireless communication at the end of the day is something we've all just agreed on, something we've agreed to follow. It's a specification, it's a standard that we've all kind of sat in a room and argued usually for about 10 years to get one of these standards ratified. And we all agree that, okay, in this frequency band, dividing that frequency band into these little slices we call channels, inside of each channel, we're going to modulate our frequency at a certain rate in order to represent data. That modulation rate is going to consume a certain amount of bandwidth. We're all agreed that this is how it's going to work. And so for frequency shift keying, at least, one of a zillion different ways to modulate that RF signal, we need at least 4 senses of time. We need to agree on what the center frequency is. We need to agree about on how far we're going to adjust the center frequency to represent a 1 or a 0. We're going to adjust it a little high and a little low to represent a 1 or a 0. These examples here are all for Bluetooth Low Energy. We need to agree how often we're going to shift that frequency to represent the data rate. So 1 megabit per second means that every microsecond we may or may not change the frequency of the oscillator. And then really important for some of these deeply duty cycled low power systems, we need to all agree on what time we're going to wake up and exchange information and then go back to sleep. These radios consume the vast majority of the active power in any of these systems, and so we want to have them off all the time, except for at the very last moment, you want to be able to go, okay, it's time, we're going to turn on the receiver, I know a packet is going to show up soon. There's always going to be a little bit of error in that estimate, and so you wake up a little early every time. That's called guard time. But you generally need a fairly accurate timer in order to schedule that. I'm mentioning these statistics here because I'm going to throw a lot of plots at you. There's going to be a red line at 20. Below is good, above is bad. So my favorite standards are Bluetooth Low Energy and IEEE 15.4. 15.4 most people have not heard of, but they have heard of Zigbee, which is the physical layer that Zigbee is. This is the physical layer Zigbee is built on top of. So it follows 15.4, and then they build their own network stack on top of it. And it's a really popular physical layer specification. A lot of IoT stuff ends up, you dig down far enough, you find out it's 802.15.4. So 20 to 50 ppm, depending on which thing we're talking about. Parts per million, if you're not familiar with parts per million, it's 4 more zeros instead of 1%. 1% is sort of 1 part per 100. You add 4 zeros, now you've got 1 part per million. It's a really narrow specification. All right, we don't have to talk about this much, but I do need to mention that the plots that are going to come up soon are Allen variance or Allen deviation plots. The big thing, the reason Allen variance is so important in this area is that if you watch the error when a frequency source shows up, so you got a rising edge, and then later another rising edge shows up with a little error, and then later another rising edge shows up with a little more error. That error increases without bound, so it gets a little difficult to figure out how erroneous your given oscillator is. What David Allen figured out in 1966 is that the difference between individual periods, that converges. So that's the magic number that we use in order to compare performance. Because that's something where the more data you take, the more accurate of an estimate you're getting, as opposed to if you're just looking at jitter, the more data you take, the more error you're going to accumulate. You're just like, I don't know when to stop. It's just getting worse and worse forever. All right, so that's Allen variance. If we use a temperature-controlled crystal oscillator, so this is kind of the gold standard if you use a really high-quality crystal. I've got this Allen deviation plot. I've got this magic 20 ppm line drawn here. You draw this line across, and no matter when in time, every microsecond, if you're talking about data rate, every 1 second, if you're talking about sleep time, no matter how long you wait, you're below this 20 ppm error. Everything's good. This is what you expect. This is why you use a crystal in a commercial wireless communication device, because it's always going to be below the spec. That's not a coincidence. The specifications are written assuming that you're using a crystal, and so that's your major constraint. That's your source of time error. I've got this inset box about the real BLE carrier drift specification because I have kind of a bone to pick with the Bluetooth SIG about this. If you read the BLE spec literally, you need 0.17 ppm error, which is not going to fly even for a high quality crystal. If you look at the error over the length of an entire packet, you need something like 21. Okay, great. That's much more doable with a temperature compensated crystal. There is a commercial company called Aeroflex that makes test equipment, and how they test Bluetooth carrier drift is they look at 50 microsecond gaps. They pair it off. They go, okay, every 50 microseconds, how far have we drifted? It's not quite what the specification literally says. Fortunately, the proof is in the pudding, and we plug this in, and we transmit with our chips, and our phones can hear it. So there's at least some demonstration that we can do to show that we're meeting spec, at least as understood by other device manufacturers. But figuring out whether everything works in theory compared to the specification, that has been a little fun. So the bottom plot here is just the same one as before with all the extraneous stuff cut out. One of the first things we designed was a CPU clock. We want to run this at 20 megahertz. It only burns 1.5 microwatts, great. But if we pipe this out to a frequency counter and we look at how erroneous it is on an Allen deviation plot, it's terrible. And that's fine. A digital system just needs a rising edge eventually. The time between each rising edge doesn't really matter. As long as that rising edge propagates through the digital fabric in a synchronous way, you don't end up with horrendous race conditions or something like that. As long as that propagation path looks good, the clock tree looks good, when the next rising edge comes, you don't really care. And you certainly would not be using this thing for RF communication, unfortunately. It would be nice if we were pleasantly surprised by this measurement, but it's way too erroneous in order to base wireless communication off of. The big innovation, the big thing that we figured out 5 years ago was that an LC tank, on-chip inductor and capacitor, over time is below the 20 ppm number. That was huge, right? What this means is that once we initially calibrate the thing to understand what 2.4 gigahertz means in the first place, and we have some optical methods of doing that and some RF methods of doing that, instead of using a phase lock loop on chip, once we do that, the error, moment by moment, while you're doing communication, meets the specs. And so we've been able to demonstrate interoperability with 15.4 devices. As I said earlier, you can transmit Bluetooth packets from this thing. Your phones can pick it up, all in large part because this plot is below this 20 ppm number. And as I mentioned earlier, we redesigned this whole thing in 28 nanometer in what I called tape-out class a long time ago. That class is now continued. We had 10 students at the beginning. I think the most recent one they just wrapped last month had 75. They've gone from 28 nanometer ST micro. They just designed, instead of one chip for the class, 2 chips. They split the class into halves. They had 2 teams, both designing an Intel's 16 nanometer FinFET process. They did some just incredible things with this. And you can imagine if you redesign this same basic digital layout in something even more aggressive like 5 nanometer, this chip is going to become kind of vanishingly small, except for the 5 octagons I've outlined here. Right? Faraday's law doesn't care about Moore's law. You're just going to have, eventually, at the limit, you're just going to have a big spiral inductor, or 2 big spiral inductors. That's going to be your entire chip. So one of the other things that our lab is pursuing is, what if you eliminate that thing? Instead of an LC tank oscillator, you switch to a ring oscillator. They're much noisier. They're a lot smaller and lower power. We're not quite there with standards compatible communication, but I have 2 new PhD students starting this summer, and I have some ideas, and by gum, we're going to figure this out. Don't quote me on that. Hopefully it works. But, so where I see this scaling to is going from, right, PCB, eliminate the PCB. Okay, now redesign it in 65 nanometer. Right, we had this research project in TSMC 65. This is all the scale up here at the top. We go from something that's a centimeter on a side, to something that's a couple of millimeters on a side, to something that's just over 1 millimeter on a side. Hopefully here we're going to have something that is a teeny dot that you can barely see, all approaching the Larson localizers from Werner Vinge's Deepness in the Sky. That's the goal here. That's my guiding light. What can we do with it in a hurry in the last couple of minutes? I think I've got 10 slides here, so this is going to be a little rapid fire. Well, we know air quality tends to go badly in summers, and we know that if the particle counter map I've got here is any indication, most of the state has no idea what their air quality is like. Can we potentially change that? Well, a couple years ago we demonstrated that we can attach a harmful gas sensor. In this case, it was hydrogen sulfide. The sensitive layer, if you really squint, the actual sensitive point are these 6 gray bars here. That's the chemical sensor. So you could coat this thing in a variety of harmful gas sensing surfaces, attach all of those to this analog front end, digitize it, transmit it out, have that be part of a multi-hop mesh network that gets all that data eventually to you. There's going to be a bit of latency, but when you're talking about gas in the air, maybe even a couple of minutes is probably acceptable. So you could scale this up and just have zillions of harmful gas sensors on here, and eventually stack all this stuff up. At the bottom, you've got a battery, you've got the single chip Motes communication device in the middle, maybe a solar cell. A solar cell at the end of the day is just a PN junction. We can make lots of those in CMOS. So why not just make the chip a bit bigger with a bunch of area that soaks up light? And then a bunch of gas sensors. My guess is to put 6 here just because I had a demonstrator on the previous slide that included 6, but lots of gases have been demonstrated. In this case, you wrap it in transparent epoxy with a little cap at the top so that you're exposing some of these sensors to air. Then you've got kind of a distribution problem. But you could really feasibly place these at 1 kilometer spacing across the entire state. I've drawn this grid at 1 sense density just to get you in the mindset of exactly how many devices that is. It's about 250,000. But a reasonable cost estimate here is something like 20 cents per node. It's about 5 cents per piece on 2 slides ago. So that's 50 grand. For a state budget, not too bad. We got to figure out how to put them out there. So my first thought is you have a drone with a BB gun that just flies a kilometer, and then they light up, right? As soon as if they're oriented up, maybe you have to fire a couple of them so that on the off chance they end up face down. Well, that's not going to light up. Maybe they turn on, and you can totally change what we understand about air quality this way. Locally here on campus, at 1 meter spacing, that's about 200,000 nodes, or 40 grand. That would be really cool. And that's something we can do with the wireless radios we have today. They will get 1 meter range, no problem. 1 kilometer on the previous side would require a redesign. We probably want to switch to something like 433 megahertz, get a little bit longer range, bigger antenna. If you don't want to distribute heterogeneously, homogeneously rather, across the entire state, maybe you want heterogeneous clumps, you could piggyback on some of our colleagues' work. Again, over in France, they just demonstrated a 103 kilometer 10 hop link with the OpenWSN mesh networking system. These chips already speak the same wireless protocol, and so as long as they're within hearing range of one of these balloons or it's something similar, then they can all group together on one of these nodes and then have this long-range hop. So you can have a bunch of clusters connected, lots of possibilities here. Little background on OpenWSN, the website, just openwsn.org. It's been ported to a zillion platforms. Here at the bottom is the interface layer, but the rest is just a standards compliant stack of network devices. So all of these, all the layers above the actual platform are universal across the hardware platforms. And at the very end, you go, okay, how do I actually port the function that turns on the radio, turns off the radio? When you port it to a new platform, you've got to figure out how the stack reaches through and actually toggle switches. But besides that, the rest is pretty bulletproof and has been ratified by ATF. Long battery life. All right, enough said. And my favorite example, personally, is that once we get below this magic 2.6 millimeter dimension, now it fits in a standard surgical endoscope. So we can go from something where we're stuck at 1 centimeter and now have something that can be implanted in the body using routine surgical tools already. If we can fit a little battery in the same cylinder, that would be fantastic. I'm looking for partners who can design little printed rolled cells that are in the same outer diameter. But if the smarts, if the brain of the device is under 2.6 millimeters, now we can start doing some crazy healthcare stuff, which is really amazing stuff, in my opinion. So that's the long and short of being able to design entirely in silicon. We can make a complete module. We can do new science. We can create new instrument platforms. This is my little plug for the open source design tools, which I'm sure this audience is no stranger to. There are a couple talks this week and about these. When I say here, I hope you saw my student Richard Atherton's talk. He came down with something, unfortunately, and had to, maybe is only going to reschedule. Maybe he'll end up giving his talk tomorrow or Sunday. But he originally had a kind of how do you get started in open source IC design today talk set up. So hopefully he'll be able to come back and give that talk. But Mohammed Qasim is one of the biggest players in the open source IC design world. And he's got a talk and a breakout session later this weekend. So if you're interested in IC design, the most accessible way to get started is the open source tools right now. That has completely changed the game. Just like moving from this kind of arcane microcontroller design world and then being able to just use Arduino and have it work and have it be much more accessible to people. The open source IC movement is doing the same thing. It used to be something that was very secretive. You kind of have to apprentice into learning how it works. It is really like horrendously complicated. It's still fairly complicated, but at least the tools are much more accessible. Anybody can just download them on their own PC in the middle of the night and get started on it, as opposed to needing to join a PhD program. So that's it. Happy to take questions. Thanks, everybody. We'll start here in the front.
So I didn't hear the word energy harvesting at all in your presentation.
Yes, that's true. Energy harvesting is it's a rabbit hole that I stay far away from as much as possible. Just because if I can draw a kind of clean break and draw an interface at VDD, right? I assume we're going to get 1.5 volts from somewhere. Then I'm happy to kind of move forward from that and do more RF circuit design on the other side and partner with folks who can do the energy harvesting stuff. That is, it's an entirely different world from my specialty that I want to identify the interface and go, if you have energy harvesting ideas, please, let's plug them in together. But you're absolutely right. Being able to harvest the energy is the key to very long-lived deployments across the state, across the world. Yeah.
Silicon MEMS oscillators are a thing these days.
Yes, they are.
They seem high power. Can you talk a little bit about why we haven't seen more of this LC stuff instead?
So, yeah, so Yeah, silicon crystals as opposed to quartz crystals, right? Companies like SciTime are absolutely destroying the field, right? They have just incredibly high performance and actually comparable power consumption, even lower power consumption versus crystals. They're still an off-chip component, so that's, versus quartz crystals. They're still an off-chip component, so I'm still interested in eliminating them. The most compelling, sort of the most sort of highly integrated product I've seen is Texas Instruments now has an integrated bulk acoustic wave resonator that provides a very highly accurate sense of time, all in one package. So that is really fantastic. It's still kind of a post-processing thing, but my suspicion is that the reason we don't see a whole lot of this compared to just go ahead and use a resonator of some kind is because they want the customers to be able to plug it in and have it work. What we need to do is go through kind of a lengthy calibration process when we power the thing on. We're optically programming it, we're providing timing pulses, it's finicky. And what companies like Texas Instruments are interested in enabling, I'm guessing, is much more out of the box. It works. The RF communication layers, right, just work. They're robust against temperature, and they're not going to be fielding a whole lot of frustrated customer calls that say, "What is going on here?" In the academic world, though, we're happy to field those calls. So, I think there was a question over here. Yeah.
What's the current like power usage on the SoC basically right now? Like what are you getting? Like, and also from that, you mentioned the power harvesting, but like, are you able to do similar tricks with, like, say, how RFID is able to like be powered by like a remote reader and stuff? Like, if it's picking up a signal from the mesh network, can it get power from that?
Right. Yeah. That's a great question. So in terms of active power in transmit or in receive mode, it's about a milliwatt, round numbers. That's one of the reasons why the slide I had to skip earlier, why the estimate that I have of scum with a CR2032 battery at sort of iBeacon level communication, why I would estimate that we're going to get something like in excess of 10 years battery life there, except for this top bullet here, which is that our leakage current level is really high. There's just some set of gremlins in the chip right now that means if we try to power off all the voltage nodes that we have, we still end up leaking a horrendous amount of current. It's something that I'm happy as an academic to sweep under the rug because it's been demonstrated so many times in industry as something that low power modes, sleep modes are kind of well understood. It's not an interesting research project. So we present this at a conference, people go, yeah, but all these other companies already do this. If we end up with enough interested student work, basically, and we can attach some more intelligent digital controller, that would be great. But the sleep current is kind of a bummer, basically, every time. We want to plug in a small battery, and the battery's just going to die pretty quickly because of the sleep current. But the active current, the differential that's consumed when we're turning on the transmitter or the receiver is still maybe 5 times-ish less than most commercial devices. And that's thanks to some really innovative RF design work done by my colleagues back at Berkeley.
What methodology are you basing your sleep mode off of? Like, how are you doing that?
Right now, our sleep mode is just definitely a hack. It is limited to downclocking the CPU.
Okay,
so sleep mode for us is
just lower than
yeah.
So
yeah,
it goes
exactly.
from 20 to like what, like 5?
From 20. It goes from 20 megahertz to 78 kilohertz. Is the lowest speed. Really put it in a deep sleep, and it's it's an atomic operation to switch the CPU clock back up to full speed, full speed. Yeah.
It wasn't clear to me how long of a time period you're saying this. You've done this research over. Is this 10 years worth of work, a year's worth of work, a month's worth of work?
Great question. So when one slide I had to cut rather than talk about this for 2 or 3 hours was the wall of people who contributed to this. This was 3 PhD dissertations, 1 postdoc, about 20 master's students who contributed, and maybe 30 undergrads all over the course of starting, I started my PhD in 2012. So something like a decade times many people contributing designs, unique designs that had to be painstakingly verified in silicon. We taped out, I think, 6 chips and finally got to something that worked with the 5th one and then made some improvements after that. Yeah, lots and lots of effort. Certainly something you're not going to rapidly prototype terribly easily, but that's something that we also really want to change. We want to make this something where it's essentially hard IP. You drop in and synthesize around it, and now you've got a radio. Yeah, but
Are you looking for collaborations with other universities, or?
yeah, absolutely. Yeah, collaborations with other universities, other institutions that can plug in complementary components and make this better than the sum of its parts. Absolutely, right? The more fantastically sci-fi-ish sounding paper possible, the better.
Okay.
I think, should I maybe cut it off and take questions offline in light of time?
Yeah.
How's that? Okay, so we'll cut things off there, but I'm happy to answer questions up here.